Hello and welcome to this clip on reviewing carbonyl derivatives and the nucleophilic addition-elimination mechanism. So we'll focus on acyl chlorides and acid anhydrides and how they actually react when in the presence of nucleophiles. This time I'm going to go into a little bit more detail of the nucleophilic addition-elimination mechanism, and I'm going to assume that you've covered the basics of carbonyl chemistry surrounding aldehydes and ketones already. But it's worth also reiterating it's an extension topic only and is not needed in detail or depth for the specification. Here we've got a range of carbonyl derivatives. Some of them are on your specification and some of them are not. The carboxylic acid, carboxylate and ester will be covered in a separate video clip, as will amides. Thioesters and acyl phosphates are not on your specification. So with that in mind, the only ones we'll really be looking at are acyl chlorides and acid anhydrides. It's worth pointing out as well that in each case they contain the carbonyl group, which is simply just C double bond O. But they won't behave as true carbonyl compounds, i.e. they won't react with 2,4-DNP and they won't react with Tollens reagent, because basically what's happening is that the other atom that's bonded to the carbon atom in C double bond O is too electronegative to allow the polarity of the C double bond O to remain as it was. In other words, if you look closely you'll see that you've got things like oxygen, nitrogen, sulfur, etc., chlorine. All of these are electronegative atoms compared to carbon, and they will affect the polarity of the C double bond O. So I've highlighted all the carbon atoms that I'm talking about. So they're all part of a C double bond O, which itself is polar, but they're also attached or bonded to another electronegative atom, which will also draw electron density towards itself. So the behaviour of the C double bond O is affected. So the reactivity of a carbonyl-based functional group depends very much on the electronegativity of the atom bonded to the carbon atom in the C double bond O, and how therefore this affects the polarity of the C double bond O. So looking at two examples, you've got an aldehyde on the left where the C double bond O is clearly polar, and an acyl chloride on the right where you also have the polarity of the C single bond chlorine. So therefore the polarity of the C double bond O on the right hand functional group is disrupted. And this brings us to another functional group that I wanted to cover in this clip. It's also worth pointing out at this stage that looking at the image it calls it an acid chloride. They're now really called acyl chlorides, and in our specification we'll be using the term acyl chloride. So the reason that acyl chlorides and acid anhydrides and such like are so susceptible to nucleophilic attack is because they actually have two different electronegative atoms bonded to the carbon. So you can see that the delta positive carbon is actually having electron density drawn away from it in two different directions, by oxygen on the one hand and by chlorine on the other. That makes that particular carbon very, very vulnerable to an attack by anything that's got a lone pair of electrons, in other words, a nucleophile. So essentially anything with nucleophilic tendencies, the essence of which means that it's got a lone pair of electrons to donate to a dative covalent bond, will tend to be attracted to this carbon atom. So this is an animation showing the nucleophilic addition-elimination mechanism. It's moving quite quickly, so I'll take you through it step by step. Basically you have a nucleophile that you can see down the bottom left hand corner of the animation sequence. And the important thing to remember is that nucleophile contains a lone pair of electrons, which allows it to act as a nucleophile. So typical nucleophiles in this instance might be alcohols containing the oxygen with its lone pair, ammonia containing the nitrogen with its lone pair, or for example amines containing a nitrogen with a lone pair. So what happens is the nucleophile is attracted to the partially positive carbon atom. That's step one. And then the nucleophile will have a lone pair which will form a dative covalent bond with that carbon atom. And the carbon atom is the one in the carbon double bond oxygen. The next thing to take place is the pi bond in the C double bond O breaks and the electron pair transfers to the oxygen, making it fully negatively charged and part of an intermediate. So we're now onto the intermediate in the middle of the animation, and a lone pair of electrons on the oxygen atom in the intermediate reforms the double bond. So the lone pair of electrons will essentially be the negative charge. So you can see the curly arrow going from the negative charge to the C single bond O that's remaining behind. That's a sigma bond. So because a lone pair goes towards the C single bond O, it now makes it back into a C double bond O. So meanwhile, what that does is it allows the C single bond X to break. Okay, so we'll assume it's a chlorine in this case, for example. And basically it removes the bonding pair of electrons between it and the carbon atom, forming a chloride ion. So we're assuming that X over here, X minus, is a chloride ion. And finally, the organic product retains the carbonyl group, but the original atom or group attached to the carbon atom in C double bond O is replaced by the nucleophile. So just for clarity, I just wanted to point out that in this particular description I've been giving you, X has been assumed to be Cl. It could clearly be any one of a number of things, and the mechanism would be exactly the same, but for the purposes of this description it's been assumed that it's a chlorine atom, then becoming a chloride ion. So reactions of acid anhydrides are similar to those of acyl chlorides, but they're less exothermic, as we've mentioned earlier on in the clip. This means that often these are favoured in industrial chemistry and in laboratory chemistry because it's a little bit safer to work with acid anhydrides compared to acyl chlorides. So we're going to have a look at what would happen if you reacted ethanoic anhydride, which you've got here, with water. It's interesting to see that on the left hand side you've actually got two ethanoic acid groups, ethanoic acid molecules. Both of these will react with each other to form ethanoic anhydride. So like we said, anhydrides will also undergo nucleophilic addition-elimination. So we start off with water behaving as a nucleophile. I've put in the two lone pairs on the oxygen so one of them can get involved in creating a dative covalent bond with one of the carbons. It doesn't really matter which of the two carbons in carbonyl groups that you choose. You've got two to choose from. So what I'm going to do is try and replicate what's going on in the image on the left, but in mechanism form. So I've chosen the carbonyl group on the left hand side of the diagram and given it its dipoles. So the water molecule approaches the carbon in the carbon double bond oxygen and forms a dative covalent bond with it, and at the same time the pi bond in the C double bond O breaks and that electron pair goes onto the oxygen. So now what happens is the lone pair that the oxygen has picked up to make it negatively charged moves back towards the single sigma bond to recreate the pi bond. So in other words, the double bond is about to be recreated between the carbon and the oxygen. At the same time, the carbon single bond oxygen will break and an electron pair will move off it onto the middle oxygen between the two carbonyl groups. and within the water molecule one of the OH bonds breaks because the oxygen is positively charged to offset the negative charge of the oxygen at the top. So the oxygen in red at the bottom, that's part of the water molecule, is positively charged. In other words, it needs to regain 2 electrons, which it does so by taking them from one of the bonds to the hydrogen. So the net result, like we've just said, the carbon double bond oxygen is recreated. You end up with an OH group bonded to the carbon of the C double bond O, and the spare hydrogen that was lost when the OH bond broke ends up bonded to the oxygen of the other part of the acid anhydride. So in other words, the acid anhydride has been split into 2 molecules of carboxylic acid, ethanoic acid in this particular case. This process is an example of hydrolysis, which is basically when water causes another molecule to break up into smaller molecules. So acid anhydrides undergo this reaction very, very easily indeed. And looking very quickly at the mechanism as to why it's nucleophilic addition-elimination, water is the nucleophile, OH is added on the left-hand side in red, and CH3COOH is eliminated on the right-hand side. So this is exactly the same mechanism that the acyl chlorides would undergo, but it's slightly less exothermic and slightly more easy to control. So let's look at applying that mechanism to an acyl chloride reacting with an alcohol. So what it might be worth doing now is pausing the video and see if you can suss this out for yourself. So I've started you off by putting the acyl chloride in, and what we now have to think about is things like dipoles and curly arrows. How would it actually end up reacting to create an ester and hydrogen chloride? So come back to the video when you've had a go at it and see if you can correct your attempt. So the first thing that happened is the nucleophile, usually alcohol, has a lone pair which forms a data covalent bond with the carbon of the carbon double bond oxygen. You'll see that the carbon has a delta plus and the oxygen has a delta minus. The next thing that happens is the pi bond of the carbon double bond oxygen breaks, and that electron pair moves on to the oxygen atom. The oxygen atom is now negatively charged, so the additional lone pair that it's picked up by taking an electron pair from the pi bond reforms the double bond. So simultaneously, because the oxygen atom at the other end of the molecule, the one that's part of the alcohol, is now positively charged, it gains an electron pair by the OH bond breaking, as shown by the curly arrow. So because the carbon double bond oxygen is reforming, the carbon would now have 5 bonds. It only needs 4, so the carbon-chlorine bond breaks. The chlorine atom takes the 2 electrons from the bonding pair. The organic product is an ester in this case, and the chloride ion that came off and the hydrogen ion that came off find each other, combine and create the HCl. From this exam style question, the first thing they're asking you to do is to write an equation. It's worth taking a moment to try and choose what kind of thing they're asking you to write an equation about. It's an ester being formed from a reaction between an alcohol and an acyl chloride. Now the acyl chloride in question is benzoyl chloride, which is aromatic. So don't forget that if you've got a line to write it on like this, there might not be room to put your benzene ring, so the way to write a benzene ring is C6H5 in structural form. So you'd have something along those lines in structural form, because that's the space that you've been given. It's not to say that you'd be wrong to put a benzene ring in displayed form or in skeletal form, it's just there isn't much space, so I'd suggest switching to C6H5 notation. So when I'm doing my mechanism, I'm taking note of the fact that they haven't necessarily said to put dipoles in or curly arrows, but I'm assuming that when they say outline the mechanism in this manner, That's exactly what they're talking about. So I'm not taking any chances. I'm going to put in the dipoles and the curly arrows. So I add my two lone pairs to my oxygen and my alcohol, my ethanol. I've drawn it in this way so you can clearly see the source of the lone pair, so you can see its role as a nucleophile. So drawing an arrow starting from between one of the lone pairs, or between the electrons, the arrow needs to point to the delta positive carbon, and then an arrow needs to start at the bond, or the pi bond, part of the double bond between the carbon and the oxygen, and point clearly to the oxygen. So I've added the negative charge to the oxygen as it's now picked up 2 electrons and gained an extra negative charge. The other oxygen was the point of bonding to the delta positive carbon, the oxygen on the alcohol I'm talking about here. So that's positively charged. So now some rearrangement needs to happen using curly arrows. First thing I do is I take the extra lone pair that the oxygen on the carbonyl now has, and I return that lone pair via a curly arrow to the carbon-oxygen bond, restoring the pi bond and therefore restoring the double bond. At the same time, the chlorine atom is eliminated, and so is the H on the OH of the alcohol. So therefore, in order to restore the neutral charge on the oxygen, this is the second oxygen I'm talking about down here, I have to break that oxygen-hydrogen bond using a curly arrow and point the curly arrow back towards the oxygen atom. And finally that produces my ester product and my side product of HCl. So the next little bit is quite deductive really. It asks you to suggest why the above reaction is a more efficient way of preparing ethyl benzene carboxylate and the alternative reaction between benzene carboxylic acid and ethanol. The way to read into this is to look at what the alternative actually is. It's a carboxylic acid and an alcohol. So in other words, it's an esterification. Now if you've done some work on esterifications, you'll know that they are reversible reactions. In other words, the reaction we've just done the mechanism for will go to completion fully, but an esterification, being a reversible reaction, might not do that. So let's now have a look at the next part of the question. It says, consider the conversion of ethanoyl chloride to compound X. Now compound X, if we look closely, has a CONH group in it. That automatically says to me amide. And what's more, could it possibly be an N-substituted amide because of the C2H5? Maybe. We'll have a look. It says name compound X, state what reagent is needed for the conversion, and write an equation for the reaction. So if it's an N-substituted amide, we need to actually name it. So I've taken the liberty of drawing out the structure a little bit so you can try and work out what its likely name might be, and it happens to be N-ethyl ethanamide. Now because it would react in response to a nucleophile, it would have to be a nucleophile as the reagent, because we've been talking about nucleophilic addition-elimination. So a reagent would have to be a nucleophile, so it would probably have to be something like ethylamine, because that's what you'd have to react with the C double bond O. So what you're thinking about here is what would you need to put that onto the C double bond O. So as per normal, I take my lone pair from the oxygen, I regenerate my pi bond to regenerate the double bond. The chlorine atom comes off, a proton comes off the NH2, not forgetting that the nitrogen is positively charged so as to regain an electron. I'm just putting circles around the charges there to emphasize them. However, the equation states that we also produce ethyl ammonium chloride. So how do we get the ethyl ammonium chloride? Well, you'll notice that we had 2 lots of ethylamine, didn't we? So that's a second reaction that now takes place. And it involves the HCl. You don't have to worry about curly arrows here because it's simply an acid-base reaction. In the same way that ammonia reacts with acids to produce ammonium salts, primary amines react with acids to produce primary ammonium salts. So simply stating the equation like that to cover yourself for the justification of the second molecule of CH3CH2 NH2 in your equation would be fine. And finally it says acid chlorides or acyl chlorides are very reactive, and they want you to suggest the name of a less reactive derivative of ethanoic acid that would react by the same type of mechanism to give compound X. And that would obviously be ethanoic anhydride. So hopefully this has been a fairly useful extension clip to take you through some of the ins and outs of the nucleophilic addition-elimination mechanism. Like I said at the beginning, it is extension. It's not intended to be a mainstream part of the specification, but it's in the textbook as an extension topic. So if you're going for an A star or you're looking for some extension work, this would be a good one to have spent some time looking at.